Okie dokie, artichokes, let's go. Okay, so the next spectra I want to talk about is mass spec. I want to explain how the machine works. You will not be assessed on how the machine works. I'm just teaching you guys how the machine works for context, just so you guys are aware of what you're looking for data-wise. So just like with IR spectra, I said the way IR works is that we have a little cuvette of our organic molecule, and we shine light through it, and then we measure the absorption of how much light it gets for those each wavelengths. So the next thing I want to talk about is how the mass spec machine works. Again, like I said, not assessed, but good to kind of understand. So similar to the IR spectra, we are going to take our sample and we're going to put it into a machine. What happens when this sample is put into this machine is that we hit it with electrons. And the reason why we hit it with electrons is so it bumps off an electron from our molecule. So if I lose an electron, that organic compound now becomes positively charged. Are we okay with that idea so far? All right. Now, organic molecules do not like being positively charged. They're not ionic. They're not ions. So being charged is really unpleasant for them. So they're not stable and they break apart. They can break apart in many different ways. So when you think about an organic molecule, it can break apart in a lot of spots. So let me just kind of draw you one organic molecule that we're going to be looking at later. Actually, let me just draw a generic organic molecule. So let's say I have 3 carbons. We'll keep it really simple, and we're dealing with an alcohol. It's just to give you an idea of how this machine is working. So let's say I have this organic molecule, and I put it into the machine. I've hit some electrons at it to knock off an electron from this molecule. When I knock off that electron, this molecule now becomes positively charged. Okay? Does not like being charged because that's not how they're designed to behave. And so they generally are unstable and they will break apart. There are lots of different ways it can break apart. It can break apart right here, and you get these 2 pieces. This is piece number 1, piece number 2. It can also break apart over here in a different, so say you still have you have multiple versions of the same molecule. So molecule number 1 has broken into these 2 pieces. Molecule number 2 has broken into piece 3 and piece 4, for example. Are you okay with that so far? When these molecules break apart, one half becomes charged and carries that charge. It still carries that charge. The other half is uncharged because it's only lost 1 electron. So half becomes charged, half becomes uncharged. Are you okay with that so far? So basically, I chop up this molecule and I have lots of different pieces. The next thing that happens is that we put this sample through a magnet, and that magnet is going to bend the molecules. If the molecules are really, really small, so if that fragment of that molecule is super tiny, like say if it's just this guy over here versus this guy, that's going to bend a lot more, whereas bigger molecules don't bend as much because it's heavier. So that's what that's representing with the with the little bits and pieces splitting up. So it's splitting it up based on size. Are we okay with that as an idea? Then I really don't like how they branded this. Now you can't actually see it as well. Then it hits a detector. So this is basically something that's just measuring what's hitting it. Now it measures the frequency of the size of item that hits it. And then it gives you this data here, which is our mass spectra data. So on the bottom here is the different masses of the fragments that are hitting the detector. If you guys remember, when we talk about atomic mass, each element on the periodic table has a set mass, like carbon's 12, hydrogen's 1, oxygen's 16. So you add up all those values, and that gives you a mass on there. So that's how I can figure out what's what. So this is based off of the frequency, and it's based off of a percentage relative to each other. So the most common fragment gets the highest peak, and then everything's in reference to the 100% value. So let's look at an example so you guys can kind of see this in action. So I'm starting to take the collated questions you guys have been looking at. Now, again, I haven't printed this off because I find that you don't really need it printed off to be able to do this. So, in question number 1, the first thing you will do is you will look at the IR spectra and you will try to figure out what that is. So, I'm looking at that real quickly. What functional group is that? I'm going to find my notes. What functional group is that? Look at your resource sheet. Look at the, I think I have mine in my bag somewhere. What's the functional group? Is it a carboxylic acid? Is it an alcohol? What is it? All right, so when I'm looking at that guy there, I'm just going to move this on so that way we know we're looking at question 1. Oh, I don't want red. I don't want black. There you go. Okay. This is question 1. I know, I'll move it over. All right, so we're looking at question number 1. So if we look at that IR spectra, here is the 2 bits of information. So like I said, you have your personal resource sheet with where you can jot down notes. One of the things that you are thinking about is, I would first check to see 1700. Do I have a peak there? Oops, wrong one. All right, if I go to 1700 over here, do I see a peak? Or should I say trough, however you want to describe it. No. So what did that tell me already? No carbonyl, so I'm going to write that down for question 1. So IR, there is no 1700s peak, therefore no C double bond O. So that's helped me rule out that it's not a ketone, aldehyde. What else has it ruled out? What else has carbonyl? Amide. What's the last one? Carboxylic acid. Yeah? Okay. So next thing that I would look at is the CH. So CH we know is roughly around 3,000 because I want to see what's around there because that's a good reference point. I can see that there's quite a big peak. I don't know why I keep calling them peaks. That's how I'm used to calling them. I know it's probably going to annoy people. I can see Bahaz looking at me like that's not a peak. We can see here that there's a peak and it's above 3,000. It's roughly at 3,500. So again, we can use our resource over here to help visualize it, and we can also use this over here. So I want to think about things that are roughly about 3,500. So I have alcohols here, and the other thing that it could potentially be is an amine. We've ruled out amines because there's no carbonyl. So I have to basically choose between an alcohol and an amine. And if I look at this sheet over here, alcohols look like this, whereas amines look like that. So from that information, I have an alcohol. Let's go back to that. So we have a peak at about 3,500. It's deep. It doesn't have the 2 teeth. Or I should say, doesn't have the double peak. So from this information here, I have ruled it to be an alcohol. Are we okay with that so far? So that's the first step with any of our spec work, is we need to figure out functional group, because that's then going to scaffold into everything else. All right. This here is the CMMR data. We're going to look at that one last. So we're going to look first at the mass spec. Now, for the mass spec, this is what I'm referring to when I say the molecule breaks apart. It hits the detector, and there's different frequencies that we get each fragment. So basically, the fragment that's most common is the 100% value. That tells me basically where the molecule is likely to break. and then still hold the charge. So this is my 100% here. We call the highest peak the base peak. One of the things you need to do for an achieved is identify the base peak. So basically you look to see which one's the tallest one. The tallest one's base peak. The other peak that you need to identify is the molecular ion, which is the line that's furthest to the right. That's the biggest mass. Now in this case, the molecular ion's really small, so I've given it to you. I said the molecular ion is 116. So what that tells you is that the mass of this molecule is 116. On other spectras, I will not label it because it's pretty obvious. So in this one here, the base peak is at, let's do some counting, 55, 56, 57. So 57 is my base peak. And then my molecular ion peak, the one that's furthest to the right, that's the biggest mass, is this one over here, which is 86. Now, something you have to keep in mind is these little teeny tiny ones are often just background noise and not actually the molecular ion, so it's not actually the molecule. If it's teeny tiny and I'm worried you might miss it, I will label it. If it's big like this, then I trust you won't miss it. So if you go through the questions, you can see that some of them are very easy to see. And in this case, the base peak and the molecular ion are the same one. This one you can see over here. So,
was it you guys being real loud?
Yeah, because we were playing Gimkit. They were playing the Snowball Zombie version.
Snowball Zombie.
I highly recommend that one.
Okay. I've got to go at 3.
Oh, let me just pause the recording. All right, I'm just trying to see one that I've given an example where I labeled it, but I think the first one's the only one that I did that. Oops. Just need your bag. What is this? This is S5. This is S6. That's one over. I'm just trying to see if there's one that I've labeled for you, and I don't. Oh, this one I've labeled. Why did I label that one? Oh, because it's hard to read in the bottom. Yeah. Anyway, so usually what I'll do is I'll give you a hint if it's really hard to read, like this one here. Okay? Then let me tell you what you're going to do to figure out what this molecule is. So let's go back to this guy. So 2 things to keep in mind. Tallest peak is your base peak, which is the most common fragment. It's usually a fragment. It's very rarely the molecular ion. And then when I say the largest peak, and when I say largest peak, I mean the biggest mass. Or the most, rightmost peak. So when you're looking at the data, this would be the rightmost peak because it's to the right. It's the last one that you see on the right. This is your molecular ion. This is really important because it tells you the mass of the molecule. And from the mass of the molecule, I can then figure out how many carbons I have. So let's start putting those 2 pieces of information together. So first bit of information, I have an alcohol. If I was to draw a generic alcohol on an N carbon, it would look like that. Correct? All right, let's add up the different compounds based off of their molecular masses. On this piece of paper here, I've annotated the common ones that you'll see in organic chemistry, so you don't need a whole periodic table. But basically, I have 1 carbon, which is 12. I have oxygen, which is 16, and then I have 1, 2, 3 hydrogens, which is a 3. So if I add all those together, I will have 31. Hopefully I did my math right. Yes, I did. Do you agree with me on that? Okay? Now, the next step is I like to play the game called adding 14. I think it's 14. Let me see. 12, yeah, 14. So the next thing I will do is I will keep adding 14 until I'm 1 away from the molecular ion. So basically until I'm 1 away from 116. So if I add 14, find my calculator because no, I can't do mental math. So if I do 31 plus 14, I'm now at 45. If I add another 14, I'm at 59. I add another 14. You're going to need a calculator for this topic. Is 73. I add another 14. That's 87. I add another 14. 101. Add another 14. I'm at 115. And now I am 1 away from my molecular ion. And the way I just add it is I add another hydrogen on the end. So that just means you have one more hydrogen, plus 1, and that's the hydrogen. Now, if I go back and I count how many times I've added 14, I can figure out how many carbons I have. So 1, 2, 3, 4, 5, 6, plus my original molecule over here, 7. So this molecule here has 7 carbons. Are we okay with that so far? So combining those two bits of information, I can make some guesses of what my organic molecule is. Basically, you have an organic molecule that's 7 carbons long with an oxygen. Sorry, with an alcohol. There are lots of different isomers that fit that characteristic. So for example, if I was to draw some isomers, 1, 2, 3, 4, 5, 6, that's one potential isomer. I could also have 1, 2, 3, 4, 5, 6, OH over here. That's another isomer. 1, 2, 3, 4, 5, 6, over here. Now it's on carbon number 3. I know. So do you see how from that information I can figure out potential isomers? When I see you guys next week, I will talk about how we can figure out which one's which based off of the last spectra information. But at this point, I just want you guys to figure out how many carbons are there. Questions, concerns, or comments? No? All right. Trying to decide if I want to tell you this last thing or not, or if it will confuse you. It is, but I might hold off until you guys understand a bit more. I'm going to hold off until you guys understand a bit more. Okay? So, we've done the notes. You guys have 15 minutes left. I would like you to start looking at these combination questions and just answer the first 2 bits. What functional group is there and how many carbons are there? And if you want to take it one step further, figure out potential isomers that it could be. And that's why we spent so much focus on isomers, because it's a big part of this standard. All right? Cool. That's us. All right. Just because I notice some of you guys are still not 100% sure what's going on, so let me just show you what I mean. Okay. All right. Oi, team. All right. This here is 31. Agreed? This that I'm adding is 14. So every time that I'm adding 14, I'm adding a new set to my chain. Now, when I get to the end here, I added 14, and then I notice when I do the math that the total is 115. I then add an extra 1 because this has an extra hydrogen, because it's at the end. So if I was to draw this guy out, it still has this bit here, which is 14. And then I add 1 more hydrogen for the tail. And that's how I get that to being 116.
Good afternoon, everybody. Sorry for the interruption. The basketball boys agree. You get a time change for your game this afternoon. You need to meet in the gym no later than 4 p.m. this afternoon. Basketball
So when you guys are looking at this second problem here, what did we figure out? What type of molecules here? Or what function group? It's a ketone or aldehyde because it has a carbonyl, but does it have an OH? No, so not a carboxylic acid. Does it have an NH? No, so it's not an amide. So we've narrowed it down. Draw what an aldehyde looks like, count the mass, and then add 14 until you get to what number? 85, and then you add 186. Give you another minute or two to figure that out, and then I'll show you the answer. All right. So, I heard one group say that there's 5 carbons in the second molecule. Anyone else want to take a stab at it? Or confirm that they got 5 as well? Still struggling? All right. So, question 2. We figured out it was an aldehyde or a ketone. So let's just assume aldehyde. That's what an aldehyde looks like at the end. And then you have a question mark. We don't know how many carbons are after that point. Let's do the math. So carbon is 12, oxygen 16, hydrogen's 1. Add all those numbers together. We get 2, 8, 9, 29. Now, just a heads up of a shortcut. Look at this. Fragments in mass spectrum. These are common fragments. You can see 29, that there's CHO, and that's representative of C double bond OH. Sorry, I'm running yellow on yellow. It's not ideal. So you see how you have some shortcuts to figure out the math? There's hints there. All right, so I have 29. We are going to add 14. That gets me 43. We're going to add another 14. That gets me to 57. We're going to add another 14. That gets me to 71. What number are we aiming for? 85. Add another 14. 85 plus 1, because that's your N hydrogen. And that's 86. Let's go through and check how many 14s we have. We have 1, 2, 3, 4, and then the original 5. So this is 5 carbons. Catherine's looking at me. Do you want me to explain that again? All right. So 29 I got from this guy over here. Right? I'm trying to figure out how many carbons to add. When I add an internal carbon, it is 14. And the reason why it's 14 is because carbon is 12, and then there's 2 hydrogens, which are each 1. So that's why I got the number 14. So I'm trying to keep track of how many carbons I'm adding. So this is my first carbon with the aldehyde. I've added 1, 2, 3, 4 carbons to that original carbon, total 5. So I'm just adding 14 until I'm 1 away from the mass, which I got from the mass spectra. And then I add 1 more, because that's my hydrogen. So now I match the number that's on the spectra. And then I go through and I count. I've added this 14, so that's 1 carbon, like that guy over here. So 1, 2, 3, 4, and then this 5. Practice this. Practice makes perfect.